Hi, we're doing a video clip on 6.3 on exponential functions graphing. This 6.3 will have two media clips because there's two assignments, but it has those. This one's with the graphing, and the next one is with solving exponential equations. Uh, so there will be another one coming with that. So I want to begin with remind you guys what the definition of an exponential function is. An exponential function is of the form c times b to the x, where b is greater than 0, b does not equal to 1. B is actually called the base. That's why I use the letter b for the base. And c is some real number. It's like a multiplier. That's the one that makes it stretch or compress. Remember when we talked about transformations. And I want you to note that all exponential functions, before you apply any transformation to them, will always go through the ordered pairs 0, 1, and 1 comma the base. So if you had f of x equals 2 to the x, it'll go through 0, 1, and 1 comma 2, because 2 would be the base. So I demonstrate that here with a couple of pictures. F of x equals b to the x, as we can see, is 1. B is greater than 1, it will look like this. It's kind of like a backwards L shape, okay? And it will go through 0, 1, and it'll go 1 comma the base. So if this was 2 to the x, it'd be 1 comma 2. If this one was 3 to the x, it'd be 1 comma 3. And it would make sense, because if this was 3 to the x, and if x is 1, 3 to the 1 is 3. So it makes perfect sense there. If you have f of x equals b to the x, where b is between 0 to 1, it'll look like this. So it looks like a forward L shape. Remember, we're not applying any transformation to this. We're not going up, we're not going down. We're just doing the basic exponential functions. So, and notice it does go through the 0, 1, and it will go through the 1 comma the base. So if the base was 1/2 to the x, it'll go through 1 comma 1/2. So it looks like a forward L. So when the b is bigger than 1, the graph is actually growing as you go from left to right, so it's increasing. And if it's b is between 0 and 1, it's actually going down, it's decreasing. So they both have a horizontal asymptote. They are actually getting leveling up towards the x-axis, one on the left side and one on the right side. So there is a horizontal asymptote, and it's y equals 0 in this particular case. If you shift it up, the horizontal asymptote will be equal to the number of shifts that you go up with it. So I gave 3 examples here, in addition to what we did in class. F of x equals 2 to the x plus 1. So the basic graph I want to graph is y equals 2 to the x. So that's why I have 2 graphs. I'm going to show you what the basic one looks like, and then I'm going to do the transformation one. So remember, it goes through 0, 1, and 1 comma the base. The base is 2. And so this one's going up, so it's going to look like the backwards L shape. And that's not the answer to this function. That's just the basic graph of 2 to the x. Now, what this 2 to the x plus 1, if you remember back in 3.5 is where we learned the transformations. And when you add 1 to the x, that's a shift along the x. And that makes everything go to the left, if you recall. If it's plus 1, it goes left. If it's minus 1, it'll go right. So the points on the graph will go all left. So the 0, 1 will be at negative 1, 1. And at 1, 2, if you move it 1 unit to the left, it's at 0, 2. Now you can get these same 2 points by just plugging numbers into the actual function. If you put in 0, 0 plus 1 is 1, 2 to the 1 is 2. If you put in negative 1, 2, negative 1 plus 1 is 0, and 2 to the 0 is 1. So you could actually find this just by plotting a couple of points. Anyway, so then the graph looks like this. But there's a horizontal asymptote at y equals 0, because it levels off towards the x-axis as x approaches negative infinity. Now the next one, this one's going to be a negative 2 times 3 to the x minus 1. So the first thing I want to do is I want to graph y equals 3 to the x, see kind of what it looks like. There's a negative 2 multiplier, but this one, and then x minus 1 is there as well. So I put in 0, and I get 1, because remember they all go through 0, 1, and 1 comma the base. Well, the base in this case is 3. So if you look at 3 to the x, so this is a graph of y equals 3 to the x, and this graph is y equals 2 to the x. You notice it's a very similar picture. They're both backwards L's. You're like, what's the difference? This one just is a little stretched a little higher. It's up 3 instead of just up 2. So if it was 1 comma 4, it would be even higher than that. So 4 to the x has a bigger steepness, more steepness than 3 to the x, and so on. So then, if you do the rest of this thing now, remember the -2 will actually shift it down. Not shift it, but flip it upside down, and the 2 will stretch it. But before you do any of that, you also got to move the thing to the one unit to the right this time. So it's opposite direction as this one. So if you look at the first step, if you just move it 1 unit to the right, it looks like this. This goes 1 unit to the right. This goes 1 unit to the right, so it looks like this. So that's what happens when you move it 1 unit to the right. And then you take that graph, the negative turns that graph upside down, and it stretches it. So instead of 1 up, it's going to be actually 2 down. Instead of 3 up, it's going to be actually, what do you think, 6 down, because it's 3 times -2, which is -6. And I might be out of room here. 3, 4, 5, 6, barely. So it looks like this. So this graph, the original graph, was moved 1 unit to the right. That's what the red one illustrates. And then the -2 will turn it upside down and stretch it. So there's actually 2 transformations being applied to this one. Actually 3, to tell you the truth. It's 1 unit to the right, stretched by a factor of 2, and then vertically reflected. So actually there's 3. And anyway, so this is the solution graph of the original function. And remember, like always, the reason you draw graphs is you're finding the solutions to that particular equation, in this case, a function, an exponential function. Now, the last one, example 3, is f of x equals 1/2 x minus 1, so it's kind of the same thing. It's going to get 1 unit to the right, but this one is going to get actually moved up 3 units. So, but first of all, before we do anything else, we're going to graph 1/2 to the x. But like I said, they all go through 0, 1. And they'll go through 1 comma the base. And the base is not 2, the base is not 3 this time, it's 1/2. So it's 1 comma 1/2. Remember, it goes through 0, 1 and 1 comma the base. So in this case, it's actually going down. So it looks like a forward L shape. So as you notice, the horizontal asymptote again is y equals 0, just like it was here and here. Okay, and here. They're all y equals 0, and including this one, because it hasn't been shifted up, it hasn't been shifted down until now. Okay, so this one we actually do a +3. So this graph right here is going to have to be taken and pasted 3 units higher than where it is right now. So instead of 0, 1, I got to go up 3 units. So it's going to be 0, 4. Instead of 1, 1/2, you got to add 3 to that, so it's going to be 3 1/2. So it's about right there. Now the graph still has that forward L shape, so all you've done is just moved it up 3 units. But here's the problem. If you look at this graph right here, it's been moved 3 units, but you wouldn't know it by just looking at it right now, because it looks like to the naked eye that this thing could actually keep going down, and you don't know that it is actually bounded by something. So if you don't draw the horizontal asymptote, I'm going to think, well, this student thinks that this graph continually go down. So you need to draw the actual horizontal asymptote to show us that you know that this doesn't get any lower than in 3. So horizontal asymptotes are really important, just like they are on the rational functions. So the only thing is, this horizontal asymptote on this side does not exist on this side. So really, you don't need this part of the horizontal asymptote if you don't want. But most students put both of them down. So now, if you notice, this graph does not go through 0, 1, okay, because it's been done a transformation. So remember, the 0, 1 and the 1 comma b only applies when you have not done a transformation yet. So, but this is a good thing to know to get the basic graph down. So if you can get this down, And then remember your 3.5 transformations. That's what we did. You know, the -1 goes to the right, the x plus 1 moves it to the left, the +3 would move it up, and so all that good stuff we did back and forth in 3.5. And put that in conjunction with this new knowledge here, 0, 1, 0, 1, 1 comma the base, 1 comma the base. Put those two topics together, 6.3 becomes really, really easy to do. So one other thing, there is another type of an exponential function. We will talk about that in class, and just so you can see it on this board here, it's actually e to the x. That is actually called the natural exponential function, and e is a certain number, and but e is actually equal to 2.71828282845 That's all I can remember off the top of my head. This is a number that's irrational, and it's used a lot in banking and things like that. And exponential growth we talk about later, okay, and exponential decay. And but this is called the Euler's function, and or we also call it the natural exponential function. So this number comes about in calculus, and that's where the number originates in calculus. It's got to do with limits, and that's kind of beyond our scope. But so E is kind of comes from calculus, whereas pi, if you remember pi, where did you first learn that? And if you think geometry, you'll be right. That's because so pi comes from geometry, and E comes from the calculus. So they're totally different numbers, and they have their own purposes. So, but you probably didn't talk about E in high school so much. You probably talked about pi a lot because you took high school geometry. So, but anyway, these are 3 examples. Again, this is not going to be a complete lecture of this. It's just kind of get the juices flowing again. So, and that's it.